All right, let's talk about the master plan, the secret template that really builds our entire digital world. We're going to dive into one of the most important ideas in all of modern programming.
But first, let me ask you a question. Just imagine you need to make 1,000 of something. 1,000 identical phones, 1,000 identical chairs, whatever. How on earth do you make sure every single one is a perfect copy? Where would you even start?
The answer? You start with a blueprint, a single, perfect master plan. This blueprint defines everything, every detail, every feature, every measurement. Once you have that, you can make 1, 1,000, heck, 1,000,000 copies, and they'll all be consistent. Now keep this idea of a blueprint locked in your head, because it is the key to absolutely everything we're about to talk about.
So let's see how this blueprint idea translates from the factory floor into the world of software. Because this exact concept, using a master plan to create lots of consistent items, is the absolute core of a really powerful approach we call object-oriented programming, or OOP for short.
In the world of code, that blueprint has a special name. We call it a class. Now, a class itself doesn't really do anything. It's just the plan. It's the set of instructions that says, hey, anything you build for me is going to have these specific characteristics and these specific abilities.
And what about the actual thing you build from that blueprint? Well, that's what we call an object. So if we have a car class, my specific blue car is one object. Your red truck is another object. They're both built from that same car blueprint, but each one is its own unique individual thing. See how that works?
So what's actually in this blueprint? A class basically defines two key things. First, what an object knows. This is its data, and we call them attributes. You know, for a car, this would be its color or its top speed. Second, a class defines what an object can do. These are its actions or functions, and we call them methods. Things like start engine or accelerate.
And when you put all of this together, the blueprints and the things you build from them, you get object-oriented programming. At its core, it's just a way of designing software that revolves around these ideas. It's all about modeling the real world right there inside our code.
But the real magic of OOP isn't just in making objects. It comes from 4 fundamental principles. People often call them the 4 pillars, and they are what give this whole approach its superpowers. So let's walk through them one by one.
First up, encapsulation. The easiest way to think about this is like a capsule. Our class, the blueprint, bundles all of its data and its actions together into one neat, tidy package. This is great because it protects the object's inner workings from the outside world and just keeps everything super organized. Next, we have abstraction. This is all about simplicity. Think about it. When you drive a car, you just use the steering wheel, the gas pedal, the brakes. You don't need to know exactly how the engine is firing or how the transmission works. Abstraction is the exact same idea in code. It hides all the messy, complicated stuff and just shows us a simple interface to work with.
Then there's inheritance. And wow, this one is a huge time saver. It basically means we can create a new blueprint that's based on an old one. So you could have a general vehicle class. Then you can create more specific classes like car or motorcycle that inherit all the basic stuff from vehicle and then just add their own special features. It saves you from writing the same code over and over and over again.
And our final pillar is polymorphism. Now, it's a big word that literally just means many forms. And it's this brilliant idea that we can ask different objects to perform the same action, and they'll each do it in their own way. So if you tell a dog object to speak, it's going to bark. If you tell a cat object to speak, it's going to meow. Same command, totally different, but appropriate result.
Okay, so that's all the theory. But what does this stuff actually look like when you're writing code? Let's check out one specific way that classes can make our code feel a lot less like a robot and a lot more like a human. This brings us to a really cool feature called operator overloading. And the goal here, just like the quote says, is to make our code easier to read. We're basically teaching the computer how to understand familiar symbols, like a plus sign, in a new context that just makes sense to us.
I mean, just look at the difference here. On the left, we're calling a function named add. Yeah, it works, but it reads like a computer command. But on the right, using operator overloading, we've taught the plus sign what it means to add our two objects together, so the code reads just like simple math. It's so much cleaner and way more intuitive.
All right, let's zoom out and take a look at the big picture. We've talked about the blueprints, we've talked about the pillars. So why has this way of thinking been so dominant in software for decades? What's the real payoff here?
Well, it really boils down to these huge benefits. Encapsulation gives us way better organization. Inheritance gives us massive code reusability, which in turn leads to much easier maintenance. And because everything is so well structured, we can build these huge, complex systems that actually stay manageable and can grow over time.
So, that's our tour of classes and objects. I'll leave you with one final thought to kind of bring this all back home. If you had to model your own life as a program, what would the main blueprints be? A person class? Maybe a job class? Or a hobby class? What kind of data and actions would they have? It's a pretty fascinating way to think about the structures that define our own reality. Thanks for listening.